the real movement of Earth through the galaxy. Many of us have grown up believing that Earth orbits the stationary sun in space. However, the reality is far more intricate and captivating. Earth not only revolves around the sun, but also hurtles through space at incredible speeds alongside our entire solar system. This movement may hold connections to some of the universe's profound mysteries. Scientific hypotheses propose that Earth's journey through the galaxy exposes us to cosmic rays, potentially causing genetic mutations and contributing to mass extinctions. Furthermore, variations in our planet's orbit around the sun could trigger environmental changes, such as another ice age. Understanding Earth's movement in the universe allows us to grasp our cosmic position better and may offer insights into larger cosmic questions, like the formation of our galaxy and our future. Consider being in an airplane flying steadily at a constant speed and altitude. From within, it's challenging to perceive your motion or speed. Galileo Galilei outlined this concept of relativity in his 1632 book, Dialogue Concerning the Two Chief World Systems. It suggests that there's no absolute frame of reference for motion, and the most relevant frame depends on the situation. Now, applying this to Earth's movement within the solar system, we see a fascinating picture. While the planets orbit the sun, the entire solar system spirals through the galaxy. Earth's orbit around the sun isn't a perfect circle, but an ellipse, with the sun at one focus. At certain points, Earth is closer to the sun, while at others, it's farther away, perihelion and aphelion. These occurrences happen at regular intervals, with perihelion around January 3rd and aphelion around July 4th, impacting seasonal weather changes. The conventional depiction of the solar system, with the sun at its center and planets revolving around it, oversimplifies the intricate movements within our planetary system. You see, the planets don't just revolve around the sun, but they also pull it in, causing it to shift. For example, the gas giants, Jupiter and Saturn, have a particularly strong gravitational influence on the sun and Earth, which causes small changes in the shape and orientation of their orbits. When Jupiter and Saturn are even remotely lined up, they have a significant effect on all the bodies in the solar system. This effect is known as the perturbation of the outer planets. Over time, these subtle changes in Earth's orbit can accumulate, leading to long-term changes in the planet's climate and overall environment. These changes are known as Milankovitch cycles. One of the aspects of the Milankovitch cycles is the change in the tilt of the Earth's axis, which shifts from about 22 to 24.5 degrees in a cycle of about 41,000 years. This change in the planet's tilt affects the amount of solar radiation reaching different parts of the Earth's surface, which in turn can affect the timing and intensity of glaciation periods, ice ages. Based on these cycles, some scientists predict that in the relatively near future, a new ice age may begin on Earth, spanning across tens of thousands of years. However, it's important to note that the effects of an anthropogenic climate change are currently suppressing Earth's natural climate. Cycles making it difficult to predict the exact timing and intensity of future ice ages. Let's face it, Earth's movement pattern within the solar system is very complex. However, its movement through the galaxy is even more intricate. The Milky Way galaxy is a massive and complex system, which includes a vast amount of stars, gas, and dust spanning across over 100,000 light years in diameter. One of the most exciting aspects of our galaxy is its rotation like a huge, spinning windmill. The galaxy's spiral arms, trail along as it spins. This rotation makes the stars and gas and the galaxy move in circular orbits around the galactic center. Earth is located in one of the spiral arms of the galaxy about 25,000 light-years from its center. In the solar system, there are only a few bodies that have to be taken into account in terms of gravity, and the Sun is the dominant celestial body in this gravitational field. In contrast, the Milky Way's gravitational field has no dominant object. Instead, everything revolves within the total gravitational fields of everything else. This makes tracking the motion of the galaxy's components our difficult but rewarding task, allowing us to learn a wealth of information about the complex structure of our galaxy. Just as Earth orbits the Sun revolves around the center of the Milky Way galaxy at a speed of about 143 miles per second, completing one orbit in almost 230 million years. This cosmic journey takes the Sun, and therefore also Earth, through different regions of the galaxy and introduces us to different cosmic environments. Interestingly, the stars in the inner regions of the galaxy move faster than the stars in the outer regions, due to the fact that the parts closer to the center of the galaxy have more mass, therefore a stronger gravitational pull. This difference in speed is akin to the way planets closer to the Sun move faster along their orbits than those farther away. Determining the speed of the Sun relative to the center of the galaxy involves searching for new young stars that have only recently formed and are therefore still in their birth orbit. Next, taking an average of how these stars move relative to us, we can deduct that the Sun is drifting forward at the speed of about 3.1 miles per second in towards the galactic center, at a speed of about 5 miles per second, and up and out of the galactic disk at about 4.4 miles per second. This small, peculiar motion has huge implications for the path that the Sun and solar system take through the galaxy, the orbit of the Sun. Around the center of the galaxy is not perfectly circular either. Instead, it follows a slightly elliptical path, oscillating above and below the galactic plane. It completes a full oscillation, approximately once every 60 million years. This movement is influenced by the gravitational pull of other stars, gas clouds, and dark matter in the galaxy. We're currently several dozen light-years above the middle plane of the galactic disk. Although it's difficult to determine exactly where the center is, since there is more matter below us than above us, the gravity of the disk slows the upward movement, and in a few million years will be about 300 light-years above the center of the disk before our upward movement slows to a complete halt, and we begin to descend. The vertical oscillation is more than just a peculiar phenomenon. Some astronomers support the Shibu hypothesis and believe that it can be directly related to mass extinctions on Earth, since the center of the disk is a more dangerous place for the solar system due to the higher density of stars and the radiation they emit. The motion of the galaxy spiral arms is not yet fully studied, but is theorized to be caused by a combination of factors. One of them is the gravity of other galaxies. In the local group, the cluster of galaxies that includes the Milky Way, a vast galaxy that encompasses our solar system, is influenced by various factors that shape its structure and dynamics. One significant factor is the presence of density waves, akin to ripples in a pond, which traverse the galactic disk. These waves have the power to perturb stars and gas within the spiral arms, potentially impacting conditions on Earth as we journey through these regions. For instance, as Earth traverses areas of higher density, the influx of cosmic rays and high-energy particles reaching our planet may intensify, with potential implications for climate, atmospheric chemistry, and even the evolution of life. Furthermore, the Sun, our solar system's central star, is not stationary, but instead moves through the Milky Way, carrying Earth and the other planets along in its wake. However, the Sun is not alone in its motion. All stars within the galaxy are also in constant motion. Astronomers measure this stellar movement in terms of proper motion, which tracks a star's visible motion across the sky over time. Proper motion provides valuable insights into the Milky Way's structure and dynamics by studying stars' relative movement and positions. Earth's orbit around the Sun also affects our perspective of nearby stars. This phenomenon, known as parallax, causes the apparent positions of nearby stars in the night sky to shift slightly over time. By observing this parallax, astronomers can determine the distances to nearby stars, aiding in our understanding of the galaxy's size and structure. Additionally, our perception of the night sky is influenced by the proper motion of nearby stars, which can significantly alter constellation patterns over years or decades, particularly for fast-moving stars. As we grasp the intricacies of our solar system's movement within the Milky Way, a broader question arises. How does our galaxy move through the universe? The Milky Way is not solitary in its journey. It belongs to a group of galaxies called the Local Group, which includes over 54 galaxies, including our neighbor, the Andromeda Galaxy. Together, these galactic companions are propelled towards a gravitational nexus known as the Great Attractor, a supercluster of galaxies located about 150 million light-years away. The gravitational pull of the Great Attractor influences the motion of galaxies within vast distances, shaping the cosmic dance of the universe. As a result, the local group is pulled towards the Great Attractor at a speed of about 373 miles per second. However, this movement is still not the last of Earth's movement in the universe. Our entire universe is expanding, and as a result, all the galaxies in it are moving away from each other. This expansion is not a movement in space, but rather a stretching of space itself. The universe is expanding at an accelerating rate, and as a result, the distance between galaxies increases over time. Despite all of this motion, we can still use the cosmic microwave background, radiation, as a frame of reference for determining our speed relative to the rest of the universe. This radiation, which is the residual heat of the Big Bang, permeates the entire universe and is almost uniform in all directions by measuring tiny variations in this radiation. Scientists have determined that Earth and our entire solar system are moving through the universe at about 229 miles per second relative to the cosmic microwave background radiation. At this point, it's no longer a stunning, prepare to be amazed by the cosmic revelation. Earth is far from static. It's a vital player in a celestial ballet of breathtaking complexity. Picture this. Our planet elegantly orbits the blazing sun, a dance it's been performing for eons. But wait, there's more. Our entire solar system, Earth included, embarks on a thrilling journey through the boundless expanse of the Milky Way galaxy, carving a magnificent corkscrew pattern as it hurtles forward at astonishing speeds. But hold on to your seats because the adventure doesn't end there. The Milky Way is just a part of a grander ensemble known as the Local Group, a cluster of galaxies engaged in an awe-inspiring cosmic tango. Together, they're drawn towards the enigmatic gravitational force called the Great Attractor, propelling them through space at hundreds of miles per second. And as if that weren't mind-blowing enough, brace yourself for the ultimate cosmic twist. The universe itself is expanding, a groundbreaking revelation first unveiled by Edwin Hubble in the Roaring '20s. This means galaxies are racing away from each other at mind-boggling speeds. In essence, Earth isn't merely a speck of rock hurtling through space. It's an indispensable cog in the intricate machinery of the cosmos, weaving together a mesmerizing tapestry of celestial movements. So, next time you gaze up at the night sky, remember, our planet's journey is but a tiny yet essential part of the cosmic puzzle that is space. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.